It is 8 a.m. There was a comment about homework question number 2 on part B. It is unclear what I mean when I say the reference direction for the Norton current is to the right. Change that to say the reference direction is down, and you should be good to go. All right, so today we're going to talk about amplifier circuits, and we're going to be very general and move towards op-amp circuits specifically as this lecture goes on, and then talk about op-amps for the next couple of days. So let's first talk about what an amplifier is. An amplifier is an electrical circuit or device which increases the magnitude applied at its input. So as a black box model, it's going to look something like this. So I'm going to call this guy a black box amplifier. And here on the left-hand side, we have our input. And I'm going to say generically that our input signal we'll call X of t, and our output signal we'll call Y of t. And our transfer function for this amplifier network will be the gain, denoted by the letter A, and it is defined as the ratio of the output divided by the input. So we can say, using this simplified model, that our output signal Y of t is simply A, the gain, multiplied by the input X of t. Okay. Another way that we'll commonly see amplifiers represented is using a functional block diagram method. And so that's just going to look like this. Where amplifiers are typically represented by triangles. And so we would apply X of t here, take our output Y of t here. Our amplifier is still characterized by the gain A, and we still have the exact same transfer function. Y of t is equal to A times X of t. So there are several different types of amplifiers that we can describe by such a simple model, actually. And so let's talk about them very briefly by creating a table. Spell input. So the most common, or at least the one that we are likely the most familiar with, takes an input voltage signal, amplifies that input voltage signal, and creates an output voltage signal. And because us electrical engineers are very boring, we call this a voltage amplifier. So voltage at the input creates a voltage at the output, and so we call this a voltage amplifier. Similarly, we can take an input current signal, amplify it to generate an output current signal, and in this case, we have a current amplifier. We could take an input voltage signal, amplify it, and convert it into an output current signal, and this would be what's called a transconductance amplifier. Or we could take an input current signal, convert it and amplify it to an output voltage signal, and we will have a trans resistance, or more commonly trans impedance amplifier. And then lastly, we have a special type of amplifier where both current and voltage is amplified, and these are what are known as power amplifiers, and they are a critical part of most audio amplifier systems. So this is our little table of the different types of amplifiers. All right. In this class, we are going to principally concern ourselves with voltage amplifiers. Not to say that we won't talk about any other types, but the overwhelming majority of the time we're going to be dealing with simple voltage amplifiers. When you get into your analog electronics classes, that's when we start to break everything down to the other types of amplifiers. So let's consider a simple voltage amplifier circuit. If at any point there are any questions, by all means, stop me. So using our black box representation, we're going to start here kind of in the middle, actually. This is our black box amplifier circuit. And we are going to say explicitly now that this is going to be a voltage gain, AV. So the A stands for gain, and the subscript V lets us know that this is a voltage gain. So it's going to have units of volts per volts, or we consider it to be dimensionless. On the input side, we're going to connect some sort of signal source. And for the sake of argument, I'm going to say that that source has some finite impedance associated with it. And over here on the output side of our amplifier, we're going to use our amplifier to drive a load. So a couple of things real quick here. The input signal of our amplifier circuit is not Vs of t. It is what I've labeled here as Vn of t, which is the voltage applied across the input terminals of our amplifier. and our output signal will be here, V out of T, the voltage drop measured across the output terminals of our amplifier. And I'm going to call the voltage drop over our load VL of T. So we can break this guy up into 3 distinct stages. We have over here our source stage, which is generating our input signal for our amplifier. Here in the middle, we have our amplifier stage. And on the left, we have our load stage where the output of the amplifier is sensed. Excuse me. So let me ask you guys a very generic question, not meant to be a trick question in any way, shape, or form. What is the desired or ideal behavior of such a system? Right. So ideally, VL of T will be simply a scaled version of Vs of T. Or to put this in a slightly different way, VL of T would be equal to A times Vs of T. That's the role of an amplifier circuit, is to scale the input signal, okay? So we are going to develop, just using this simple circuit, a model for our black box amplifier that will contain circuit elements, okay? And this model is actually pretty great because it's going to contain a whopping 3 circuit elements, but it'll be representative of practically any and every voltage amplifier that we could ever want to consider, including operational amplifiers with a little bit of modification. And so we'll develop this, and then I'll show you exactly why we're going to use this model as opposed to the actual internal circuitry of an op amp, okay? So if we were to disconnect our source section of our amplifier circuit that I've drawn here and look in, what would we see? What would the Thevenin equivalent be? So we disconnect everything to the left of that dashed red, leftmost dashed red line and look in. What do you think we should see based on our limited knowledge of Thevenin and Norton equivalent circuits? We have no independent sources whatsoever. So what should we probably see? Are you putting the load? Sure. We'll see a circuit. Thevenin and Norton equivalent circuit. We're looking in. What do we see? We have no source, so we should see a resistance, right? If we have some black box connected to a voltage source and we disconnect it from the voltage source, look in, we're just going to see a resistor, okay? We have no reason to believe there is, at least looking in from that direction, right? So let me think of a way to explain that. That's a fairly reasonable question. There's no voltage source. The comment was there's no voltage source inside of the black box amplifier. In truth, there are voltage sources connected to it that are not the source, meaning that there are power supplies, connections, and all that kind of good stuff. But from the perspective of the source looking in, all we're really going to see is what's called the input resistance of the amplifier, okay? So if we look in, we see an input resistance. So I'm going to start to redraw this guy a little bit. Here's Vs of t, here's Rs, and when we looked in, we observe some Thevenin equivalent resistance, Rn. This is still our voltage drop, Vn of t. This is still our voltage, V out of t. Okay, so now let's go back to our original circuit here up top. We disconnect our load impedance from the right-hand side and look in through the output terminals. What should we expect to see? A Thevenin equivalent, which is just a voltage source in series with a resistor. So I'm going to model that like this. We have some resistance, which we're going to call R out. And I am going to use a dependent voltage source. I'm going to say it's A times Vn of t. Excuse me. The reason I'm using a dependent voltage source is because I know that there needs to be some coupling between the input and the output, right? Because the whole point of this thing is to scale up our input signal. And so that dependent voltage source is doing exactly that. It's taking our input signal and making it bigger. That's all that dependent source does. So I'm going to put a box around this guy. And I'm going to call this the practical amplifier model. Technically, this is only the practical voltage amplifier model. If we had a current amplifier, we would have a current source. If we had a impedance amplifier, we'll still have a voltage source. If we have a transconductance amplifier, it's a current source. So depending on what our output signal is expected to be tells us whether or not we're going to have a dependent voltage source or a dependent current source. Not particularly important now, but when we get into our transistor circuits and simplifying them, it'll be very, very important, okay? So we can see that our amplifier and any amplifier can be characterized by three parameters. Rn, R out, and the gain A. All right, so before we move along here, I want to open up another file real quick if I can find it. This is the data sheet for a very commonly used general purpose amplifier. Here we go. This is the simplified model for the internal workings of that very common, very basic op-amp. It contains 22 transistors, 11 resistors, 1 diode, and 1 compensation capacitor. If you were asked to analyze a circuit like this at this stage in your circuits career, you would change your major, 100%. And I wouldn't blame you one bit. Literally within 1 year's time, you'll understand what 80% of this thing does. That's what your electronics classes are all about. But until we can learn how to linearize nonlinear circuits containing all these pesky transistors and all this kind of stuff, our practical op-amp model will actually do a very, very good approximation of the behavior of this thing. So we have a circuit that contains, in its simplified state, 35 components, and we were going to analyze it as if it contained 3 and still do a pretty damn good job of it, okay? So that's why the practical op-amp model exists, because this is a nightmare. All right, so we need to ever so slightly modify our practical amplifier model to accommodate op-amps. And the reason for this is because an op-amp is what's known as a differential amplifier, in as much as it has 2 input signals. And so we have to be able to accommodate that, okay? So let me draw a line here. Our practical op-amp model is going to look something like this. So we still have our input resistance, Rn. We still have our dependent voltage source. We have our resistance R out, but now we're going to be measuring everything in reference to ground. Like so. So between this terminal and ground is how we measure our output voltage. So I'm going to call that V out. Actually, I'm not going to say it's a function of time. It may be, but I'm just going to generically call it V out right now. And I need to define a couple of other things here real quick, okay? So the first thing that I'm going to define is I'm going to label this guy right here, this input, V plus. And this is for the non-inverting input signal. I'm going to call this guy down here V minus for the inverting input signal. These are nodal voltages measured with respect to ground. And the difference between these two, I'm going to call my differential signal VD, lowercase vd, okay? So what the dependent source does in our practical op-amp model is it takes what's called the open loop gain, or the characteristic gain of the amplifier, and multiplies that by that differential voltage VD to create our output signal. So this circuit is how we are going to look at what we saw back in circuits 1 as a simple triangle like so. So these two models are interchangeable. Before we move on here, I'm going to introduce something else that we effectively ignored in circuits 1. And I'm going to explicitly draw here power supply terminals, okay? So I'm going to call this guy VCC plus, representing where we connect our positive power supply voltage. And down here would be VCC minus. Which is our negative power supply voltage. Now, our practical op-amp model does not contain in any way, shape, or form our power supply voltages. And that is one of the fundamental drawbacks of this model, but our ideal model that we used in circuits 1 didn't either. The reason why I'm explicitly drawing the power supply voltages is because our operational amplifier cannot generate output voltages that exceed in magnitude our power supply voltages, meaning V out can never be greater than VCC plus, or it can never be more negative than VCC minus. And we're going to see what the ramifications of that are with a simple model, okay? So, how much space do I have here? Let me go to the next page. So let's say that I want to analyze the following circuit. Where I have connected a 1-volt source to the non-inverting input terminal. I'm going to explicitly show that I have power supply voltages of plus and minus 10 volts. Here's my output terminal. So this is my output, V out, measured with respect to ground. I'm going to characterize this op-amp by its 3 parameters of importance. My open loop gain, AVOL, and we're going to say that it is 100,000 volts per volt, which if we looked at our MUA 741 op-amp datasheet would actually be low, or less than typical for that particular type of amplifier. So 100,000 for our gain is actually kind of low. Our input resistance, let's call that 1 mega ohm. And our output resistance, let's say, is 25 ohms. So this input resistance of 1 mega ohm is actually fairly characteristic, actually maybe a little bit small for a bipolar junction transistor based op-amp. For a MOSFET based op-amp, it's about 1,000,000 times too small. Our output resistance of 25 ohms is actually a little bit larger than what we would typically see. So I'm breaking this down to something that's less than ideal, and we're going to look at how it behaves. Okay. So if we wanted to analyze this circuit using our practical op-amp model, I'd need to redraw this guy, right? I'm effectively taking everything connected to the triangle and then reconnecting it to the model that we just developed a few minutes ago. So that would look something like this. Here's Rn. This is how I typically do it, as I start with the practical model, and then I connect things as is necessary. So here's AVOL times VD. All right, so let's start with my output, just because that's really trivial at this point. Is there anything connected to the output pin of my op amp in my topmost drawing here? No. So I can say that my output voltage is just the open circuit voltage between my output pin and ground. Nothing particularly fancy there. For my inverting input terminal, which is this guy on the bottom, I have a connection to ground, right? So I'm just going to draw a short circuit to ground. And then for my non-inverting input terminal, I have a 1 volt source connected between the non-inverting input terminal and ground. So this is V plus up here. Here is my 1 volt source. Right? Anything not making sense for how I've redrawn this? Let's start there. Okay. It really doesn't get much harder than this. Feedback will slightly complicate things, but not too terribly much. All right, so what is our expected output voltage based on this model? Any thoughts? So VD is 1 volt. Okay, so let's write that down. VD is 1 volt. Absolutely correct, because it's the difference in potential between the inverting input terminal and the non-inverting input terminal, or other way around, non-inverting minus the inverting, excuse me. So we know what VD is. Should we observe any current flowing through our resistance R out? No, because it's not part of a closed current carrying loop. So no current will flow through the resistor R out, which means no voltage drop occurs over the resistor R out. So that means that V out is just AVOL times VD, right? Just using good old Kirchhoff's voltage law. So V out is AVOL times VD, which is 10 to the 5 volts per volt times 1 volt is 100,000 volts, according to our practical op-amp model. So this is where that not having our power supply connection shown gets us into a little bit of trouble. Because if we looked at this guy, we could say, great, we have a simple circuit where we can convert 1 volt into 1,000 or 100,000 volts. Awesome. But unfortunately, we can't actually do that. Practically, this is incorrect. Because this voltage exceeds our power supply voltage, V out will actually just saturate to VCC plus, okay? This is what's known as saturation distortion. In a real op-amp, the output voltage cannot exceed the power supply voltages. And so I can create kind of a piecewise definition here. All right. So V out will be VCC plus when our open loop gain, AVOL, times our differential voltage, which is V plus minus V minus, is greater than or equal to VCC plus. We call this positive saturation. On the opposite side of the spectrum, our output voltage will be VCC minus when AVOL times V plus minus V minus is less than or equal to VCC minus, or whenever it's more negative. We call this negative saturation. And in the middle is the actual only point, or series of points, I guess, where the amplifier is actually amplifying the input signal. So our output signal will be AVOL times V plus minus V minus when VCC minus is less than AVOL times V plus minus V minus is less than VCC plus. And this range of operation is known as the linear region of operation. So graphically, I want to describe what's going on here. Okay. So here is V out. Here's V in. And let's say that up here is VCC plus, and down here is VCC minus. So what we are going to observe for our input versus output relationship for an open loop amplifier, like we're dealing with here, is something that's going to look like this. Trying to draw a straight line as best I can. Okay. So everywhere to the right where it flattens out, positive saturation. And it's called saturation because an increase in the input voltage does not cause a complementary increase in the output. So it saturates at a specific value. So it's going to stay at VCC plus until we bring that input voltage lower, or until we bring that input voltage to a place where the linear region occurs. Over here on the left-hand side, we are going to have negative saturation, as we talked about before. And then in the middle is our linear region, or our linear range. So let's mathematically define our linear range, okay? So the linear range is the region of op-amp operation where the output signal is a scaled version of the input signal. Or it's the region of operation where the amplifier actually behaves like an amplifier, right? Everything else is nonlinear, okay? So our linear range mathematically, I guess I'll do it on another page, is defined as VCC minus divided by the open loop gain AVOL. So when VD, our differential voltage, is greater than that quantity, and our differential voltage VD is less than VCC plus over our open loop gain, this is our linear range, okay? So for our previous example, VCC minus was what? Negative 10 volts, okay? So we'd have negative 10 volts divided by 10 to the 5 volts per volt is less than VD is less than positive 10 volts over 10 to the 5, giving us a linear range of negative 100 microvolts is less than our differential voltage is less than positive 100 microvolts. Okay. So our linear range, when we have a very large open loop gain, is traditionally pretty darn small, right? We're talking about 1/10 of a millivolt plus or minus, okay? So this slope that I've drawn here is actually greatly exaggerated. It's going to look in practice like an almost perfectly vertical line for an open loop amplifier configuration, okay?
Will VCC plus and VCC minus always be equal and opposite?
No. So that's a fantastic question. So the question was, will VCC plus and VCC minus always be equal and opposite voltages? And the answer is no. So let's look at the restrictions on power supply voltages just for this particular amplifier, the 741. I gotta find them. All right, yeah. So here are the absolute maximum ratings, and the first thing that's listed is the supply voltage, okay? So the minimum voltage is negative 18 volts, and the maximum voltage is positive 18 volts. So as long as your VCC plus is 18 or less, and the magnitude of VCC minus is 18 or less, this guy will work, okay? So you could do it as VCC plus is 5, and VCC minus is negative 10. You could technically do it as VCC plus is 12 and VCC minus is 5. There's no reason, the only real restriction here is that VCC minus needs to be less than VCC plus. If that isn't the case, it won't work right. But other than that, you're good to go. I've seen students using LT Spice improperly set things up to where VCC plus and VCC minus are actually the same voltage, and then they don't understand why it doesn't work, and it's because you have zero linear range. Inherently, if VCC plus and VCC minus are the same thing. That's a fantastic question. We'll have example problems in the homework assignment that you're about to be assigned where the supply voltages are not equal and opposite. And that is going to obviously alter your linear range, and it's also going to alter the shape of your output signal, right? So let me graphically explain what I mean by that just real quick, okay? So let's say, for the sake of argument here, we're going to be looking at this circuit. And I'm just going to call this Vn as a function of time. Let's put this voltage to be positive 10 volts, so VCC plus to be positive 10, VCC minus to be negative 5 volts, and the out as a function of time we know will be 12 cosine omega t volts. Okay. So if we were plotting our output voltage as a function of time, so let's see. Trying to draw this to a scale as best I can. So this is time measured in seconds. This is V out measured in volts. If we were to ignore saturation distortion, in this case, our output signal would look something like this. Where I'm trying to draw a sinusoid as not crappily as possible. All right. So this is positive 12, and down here is negative 12. With saturation distortion included, this is positive 10 volts. So what we would see is that our output signal cannot exceed that value, and negative 5 volts would be right here. So what this would look like, I'm going to draw with saturation distortion in blue. So we would have something like this. Well, shit, that did not do what I wanted it to do. So our waveform effectively just gets abruptly cut off. We call this clipping. You may have seen something that looked like this in the mini lab experiments on op amps back in circuits 1, depending on how meticulously you followed the directions. So if you didn't set your supply voltages up correctly, your waveform probably looked something like this, where the peaks got chopped off and all that kind of stuff. And it's because you didn't have your power supply voltages set highly enough to accommodate for the amplification of the system, okay? So this would be what's considered asymmetrical clipping, because it doesn't, the magnitude of the clipping is different on each side of the positive cycle and negative cycle. It does, and that's actually a very important thing here, okay? So in this particular circuit, I've chosen a gain, well, I mean, I didn't tell you exactly what the input signal is at all. I just told you what the output signal is. We would see if we fed a, let's circle back up here real quick. If we fed in a 1 volt, actually, this will be a great place to do a simple LT spice simulation, because you have on something that's actually pretty fantastic. And we are going to spend the entire next class period talking about this specialized circuit. But we can introduce some things real quick. The people on Zoom, can you see LT spice?
Yes, sir.
Okay, thank you. Let me get my mouse real quick, or this will be a total pain in the butt. All right, this will be the last thing that we're going to do today. So let me move this where I can see it. No, I don't need a diode. All right, so I'm going to use what's called universal op amp 2. I use this for op amps for a very specific reason. So I'm just going to go ahead and drop this in. Now, a couple of things that I want to point out here. For this particular op amp model, the inverting terminal is the one on top, the non-inverting terminal is the one on bottom, and then the positive power supply voltage is on top and the negative power supply voltage is on bottom. So it's a little backwards, so you got to pay attention to that, okay? The reason why I use this op amp model is that if I right click it, it has a list of editable parameters, okay? So the first editable parameter is the spice model, okay? So at level 2, this is a, let's call it an ideal op amp, except that it takes into account saturation distortion, meaning the power supply voltages matter. Level 1 treats it as just an ideal op amp, so no power supply voltages matter or anything like that. The input resistance is infinitely large, the output resistance is infinitely, or 0, I guess infinitely small, and the gain is infinitely large. And then spice levels 3 and 4 start taking into account some of these parameters. So this guy right here, AVOL, is the open loop voltage gain, which is why I call it AVOL, okay? Right now it's set for 1 meg, which is the same as 1 million. So I could edit this to be 100K, which is what our example problem has. Then it has GBW, which is called the gain bandwidth product. That isn't going to matter for us for quite some time. The slew rate isn't going to come and bite us in the butt for quite some time either. Then we can limit the amount of output current. We can say whether or not it is a rail-to-rail op-amp or not. So what that means is that in a real op-amp, previously I said that the output voltage can never exceed the supply voltages. That's true for a rail-to-rail op-amp. For a non-rail-to-rail op-amp, there's actually a specific offset voltage below the supply voltages that you can exceed. So if you had a rail voltage of say 1 volt, that means that if your power supply voltage was VCC plus was 10, your output could never get larger than 9 volts or something like that. In this class, to make it not confusing, we're always going to be dealing with rail-to-rail op-amps. So we say that there's a hard cutoff at VCC plus and VCC minus. And there are certain practical op-amps that are designed that way, but there are others that have a little bit more limitation. Then we can include offset voltage, which we're not going to talk about this in this class, but will come bite us in the butt in analog electronics 2. Phase margin, I don't remember what EN, ENK, or anything like that are. This is our input resistance, or excuse me, our input resistance here is RN. So there's a whole bunch of editable parameters that we can mess around with. Yeah. So I am going to drop in several voltages. Okay. And I'm going to put them over here. It may seem weird at first. And so these guys are going to be my supply voltages. I link them up like that, and then I put ground in the middle. So let's do positive 10 volts on this guy, let's do negative 10 volts on this guy, just for the sake of argument. And then what I'm going to do is I'm going to label this top node, or the positive polarity terminal of the voltage source V1 as VCC plus. And what I can do is I can then tie that voltage to the supply voltage terminal on my op-amp. And so what I just did there, it isn't intuitively obvious, whatever voltage is generated by the source on the left is now applied to that terminal on the op-amp. So instead of having to have a crazy op-amp circuit with lots of different power supplies attached to it, I've now forced that particular terminal voltage to be VCC plus. So to me, it makes for cleaner schematic diagrams, which is why I do it. It's a little easier to see what's going on, or at least I consider it to be a little easier to see what's going on. So I can do a similar thing. I can say that we have VCC minus. Actually, VCC minus, there we go. And I will attach that to the negative supply voltage. I'm going to put another voltage source here. I'm going to make this guy a sinusoid. So I'm going to go into the advanced settings, click on sinusoid, and I'm just going to give it an amplitude of 1 volt. A frequency of 1 hertz, and I don't need to fill out anything else. So every 1 second, this guy will go through 1 cycle. And now I'm just putting some terminals here that I can attach voltages to. So let's see, let's call this guy Vin. So I'm applying my input signal, and I'm going to apply it to my non-inverting input terminal like we did in the previous example. I'm going to ground this guy here, and I'm just going to call my output voltage the out for simplicity's sake. So this is the circuit that we had analyzed. And we're, instead of putting a DC input voltage of having a magnitude of 1 volt, we're now putting an AC input voltage with a magnitude of 1 volt. And I'm going to run it for 5 cycles, just for the sake of argument. So if I look at my input voltage, I have a nice simple sine wave that does exactly 5 cycles in 5 seconds because I set it up for 1 hertz. If I look at my output voltage, you are 100% correct. We have generated a square wave. This open loop configuration is how we can convert sine waves to square waves. And the height of the square wave is entirely dependent on our supply voltage. So I just wanted to show you that because you are 100% correct when you said, I bet this is going to look.
Are the bars completely vertical?
So, okay, so that's a fantastic question. Why are the bars completely vertical? They aren't. They just look like that because the linear range of this amplifier is so small. And so I can prove that to you, okay? So let's look at .9999 seconds and 2.0001 second. It's starting to, this is not looking remotely like what I expected it to. I was expecting it to be much more vertical here. Let me change it. But the short answer is that it is not. It just looks like it is because the linear range of this guy is so small. There we go. That one looks better. So there is a actual amount of time it takes to transition from negative saturation to positive saturation. But when we're looking at things on a macro scale on the order of volts, that linear range of only, negative 100 microvolts to positive 100 microvolts is so small on that scale that those lines appear effectively vertical. So it's not a true square wave, but a true square wave isn't a true square wave either because it always takes time to switch from the negative half cycle to the positive half cycle. So it's as good as we're going to get. Any other questions about what we've talked about today or the simulations or anything? All right, so when we reconvene tomorrow morning, we are going to more formally go over what are called open loop op-amp circuits. And we're going to talk about some of their applications as analog to digital converters and things like that. And then we're going to talk about different ways that we can bias them and all that kind of good stuff as well. To be entirely honest, we're probably going to finish 30 minutes early tomorrow. Just because the different ways that we can use a ludicrously high gain is actually pretty limited. Why negative feedback op amps have much more use because we can set a gain to a specific value and do lots of things with it. With these guys, we're just stuck with whatever gain the op amp has. And typically it's really, really large, which means we have a really, really small linear range, which means it's how can we get as creative as possible about the ability to generate a square wave and use it for something. So All right, so that's enough out of me for today. I will post a homework assignment for you guys on this material within the next hour or two. I want to finalize some things and double check so I don't have any more silly typos and stuff like that. And it'll be due in a week's time and all that kind of good stuff. So I'll see you guys on tomorrow.